Alright, we're back. We can wrap up lesson 6.1. We just introduced Euler's methods into the last video, which again we said is a way to approximate values of a function without the function itself, rather with the antiderivative. Now, if we look at this differential function here, dy dx is x plus y, that's actually not too complicated a differential equation to solve, and it gives us an initial condition of 2, 0 if you plug in 2 for x, 0 for y. So we could take time if we wanted to do the differential or the antiderivative and then use that antiderivative to find f of 3, but really Euler's method, while it's not perfect, is actually very, very accurate in prediction. So here's what we start with. We have a table. First column is xy. Then we find the value of the derivative at xy. Then we will figure out what the delta x is, and we'll tell you how that is found in a second. This part right here is a variation of slope. If you divide this delta x over here, you would have delta y over delta x, which is a slope definition. Dy dx, which is a derivative, is also a slope definition. We've just solved for delta y. So we take the delta x times dy dx, which is these two things multiplied together. And then what that gives us is an approximation for the next point that we would use, the next linearization point, x plus delta x, y plus delta y. So we start with 2, 0. X plus y would be 2 plus 0, gives us 2. Now, the delta x here is 0.2. How do I get that? Well, that's given in the problem right here. I'm going by 0.2 increments along the x-axis as I move over all the way up to 3. Now, delta y, again, is these two things multiplied together, so that would give me 0.4. And then x plus delta x, that would be 2 plus 0.2. Y plus delta y would be 0 plus 0.4. And so we have this part right here. Now, this point comes down here, and that's our next starting point, and we repeat the process. X plus y. Notice delta x is the same. It does not change within the problem. Multiply these two together. 0.52, add, and that gives us our next point, which starts the next one. And I keep going, and I keep going, and I keep going. So the question is, when do I stop? Well, notice what I'm doing on my x's here, 2.2, 2.4, 2.6, 2.8. I'm moving to an x value of 3. So the next one I get right here will be my final answer. So x plus y, add those two together right there. Delta x is still 0.2. Multiply those. We have that. X plus delta x, y plus delta y gives me this. So according to this, if on my function, if I have a function whose at 2 the value is 0, then on that same function, given this differential equation, at 3 that function should be equal to about 3.46496. Now let's see what graphically we have done. Graphically, this is what we have done. The blue line represents the actual function. The black line with the points represent the points that we were obtaining doing Euler's method. Now again, notice that it is not a perfect fit. It does not fit perfectly on the line. And the further we go, the further off it'll get, because every new increment gives us a little bit more error. But you see it's still very, very close. It's still following the line very, very close. So we come here to do one final problem. Dy dx is 2x minus y. Y is 3 when x is 2. There's our initial condition. And this one wants a value of 1.5 with 5 equal steps. Alright, so we start out with 2, 3. The dy dx is 2x minus y, so it would be 4 minus 3 is 1. Now, what's the delta x on this one? Well, I need to go from x equals 2 down to x equals 1.5. And I need to do it in 5 equal steps, which means each one is going to be worth negative 1/10. Alright, delta y is dy dx delta x, so we multiply these two together. X plus delta x, y plus delta y is right there. Now I'm going to go ahead and fill in this table. If you want at some point, you can pause it and fill in your table yourself. And our last one here, if we keep going with Euler's method, we do end up down here at 1.5, 2.61051. And that is all, ladies and gentlemen. We'll answer any and every question you have tomorrow in class.